Hi everyone. My name is Ryno Visser, and as I said, I'm from Stellenbosch University. I'm a master's student in mechatronic engineering, and today I'll be presenting our paper titled "An Architecture for the Integration of Product and Production Digital Twins in the Automotive Industry." So just a quick overview of the presentation. I'll just provide some relevant background information, and then that leads into the main objective of the paper. I'll then just discuss some of the highlights from the related work section. That will then lead into the architecture and just discussing some of its components, and then also how the components interact with each other through an illustrative example. I'll then just do a quick I'll discuss some of the preliminary evaluation results and then just conclude at the end. So Industry 4.0 is characterized by the digitization of the manufacture, or the digital or physical and digital worlds within the manufacturing environment. Now, digitalization has attracted significant interest throughout various sectors, but specifically the automotive industry. Now, the concept of a digital twin is, I guess, widely recognized as being a key enabler for this migration towards a more digitized environment, and then, I guess, ultimately Industry 4.0. Now, digital twins have traditionally been applied to more product-centric use cases over the years, but over the last couple of years, the scope of digital twins has include much more than just the products. For example, complex production systems, production facilities, manufacturing processes, and so on. Now, within research and definitely within industry, there's a lack of integration between these digital twins, and a lot of research argues that this integration would allow for better product explainability or product quality explainability, and then also process traceability and optimization, using feedback from the production-related digital twins to be able to take faulty products, and then also enabling new use cases such as digital product passports. For example, one of these is the battery passport, which is a new regulation being imposed by the EU for high-voltage batteries in electric vehicles. So, therefore the main objective then of the paper is to present an architecture for a system of digital twins that integrates product and production data into the relevant digital twins within a large automotive enterprise or manufacturing enterprise. So for the related work section, for the different digital twin categories, I'm not really going to speak about the digital twin prototype, instance, and aggregate, as these are quite, I guess, well-defined concepts, but one I would like to focus on is the type digital twin aggregate, or TDTA, which is a specialized digital twin aggregate that aggregates a large number of similar digital twin instances. So what I mean by similar is firstly the physical twin being similar, but then also the types of data that the instance uses, the services that it uses, the functions that it performs, and so on, and then also the resources that it uses. So this is in place to address scalability in these types of systems where there could be potential thousands of similar instances. So in this scenario, the TDTA could then perform functions on behalf of the digital twin instance just to reduce the resource utilization. Then on the digital twin applications, so as I mentioned earlier on the product side of things, the paper just discusses some applications on product digital twins, but then also how it's been applied to processes such as maybe a milling or additive manufacturing process, but then more importantly, the integrated product process digital twins. So it just discusses some of the different methods of integrating digital twins. So for example, one of them is developing digital twins for the products, the processes, and operational digital twins, and having all of them interconnected. But then also another approach would be similar to like a shop floor digital twin, where it's a larger, more integrated digital twin that has a perspective of all the different types of digital twins in one integrated view. And also on the right-hand side, so I'm not really going to explain the reference architecture too much. I'll later on discuss some of the components and how we used it in the developed architecture, but it's a reference architecture for a system of digital twins. Then just also on the data integration methods. So in this scenario, there is a potential large number of different sources that data needs to be integrated from to develop this digital twin system. Now, data integration can be realized through a variety of methods, but for the most part, these methods will lie somewhere between a warehousing and virtualization approach. Now, on the warehousing side, it's, I guess, quite similar to the traditional ETL concept where data is extracted from the relevant sources, transformed, and then loaded into the warehouse. And then on the virtualization side of things, or in research, it's quite often also referred to as data federation. The data remains within the different sources and is only accessed when needed at query time. So in order to do this, there's a couple different components required. So one of them being the wrapper, which is a software component that manages all the interactions between the sources and the warehouse, and then also the semantic mapping, which describes where the data can be found from, what the data looks like within the sources and so on, so that you can query it. So yeah, then just onto the developed digital twin architecture. So the architecture conforms to the C4 model. So mostly for the diagrams in the presentation, it will be components and a container. And as I said before, it is based on the reference architecture I introduced in the related work section. So just to explain some of the components, I can't really go into too much detail. The paper does a bit more. At the bottom, there's the 3 different types of sources that's identified. So these are just the sources that's been identified for this use case. So you have your assembly, component, and production sources, and I'll get a bit later to what that entails. Then each source requires a source adapter. So in a sense, it's similar to a wrapper component, which it manages all the interactions between the sources and then also the digital twin hierarchy. So it has a bit more added functionality than the traditional wrapper, with the paper just also discussing a bit of the internal architecture of it. Then just also on the management services, so these are the services that the other components within the architecture uses just to ensure that architecture and all the components performs how they were intended, performing efficiently and so on. And then also can be used to ensure that changes don't propagate throughout the system. So when a new digital twin is added to the hierarchy or the current one is changed, that can just be documented within the digital twin directory. Then onto the services network. So this houses all the services that's not specific necessarily to a digital twin. It's a more general set of services. So in this scenario, the only 2 that's been used is a recall service and a notification service, but in a sense, it can include many more services using a service-oriented approach to develop services depending on the use case. Then also just the gateway service manages all the interactions between the different endpoints that's been developed and then the rest of the system. So these endpoints can be, for example, 3 dashboards, configuration, monitoring, and information dashboard, and then also the API service, which in a way is a sort of intermediary endpoint to external data endpoints that can't directly interact with the gateway service. So yeah, and then just before I get to the digital twin hierarchy, I'd just like to describe the physical decomposition, so how we went about developing the hierarchy. So first of all, on the product side of things, we used a couple different definitions from some ISO standards and a couple of NIST documents to describe a product as being either an assembly or a component, where assembly is a product that contains other products, so either sub-assemblies or components, and a component is sort of the lowest level of the hierarchy of products. But it doesn't necessarily mean that the component is a simple product or not complex. It just depends on what the context that the product is used in. For example, if you buy a pump from a supplier, that supplier might see the pump as being a complex assembly in its own right, but the company that buys it just sees it as a single component that you add to the product hierarchy. And then just also onto the production side of things. So it's based on a couple manufacturing ontologies and data models that describe a facility as being either an enterprise, factory, cell, shop, or station, with the enterprise being the highest level of the facility and the station being the lowest. Then at each level of a facility, it can contain possible manufacturing resources, maybe something like a spot welding machine and so on, that performs processes onto the products. So for example, performing a spot welding process. So yeah, now using that physical decomposition, the product hierarchy has been constructed into 4 types or categories of digital twins and in a process data model. So the 4 categories are product digital twins, executive process digital twins, the resource digital twins, and then a facility digital twin. So for a product digital twin, it can consist of being either an assembly or component, as I mentioned before. And also additionally, each product that undergoes a specific manufacturing process requires a process model, which is on the left-hand side. So the process model can be queried by the different product digital twins and can in a way be used as a view into the production-related digital twin. So this separates the concerns and localizes, I guess, the scope of the digital twin. So the product digital twins can remain product-centric and the different production digital twins can also remain to their scope, but the process data model can then be used as a perspective into the different digital twins. So for example, a specific product can use its process data model to determine which process was performed on it, which resource was performed the process, and in which facility the process was performed. So yeah, then just the process, digital twins, they want or mirror all the manufacturing processes performed. So as I mentioned before, maybe something like a spot welding process. The resource digital twins mirrors any manufacturing resources that's needed. And then finally the facility digital twin, which is the highest level of digital twin in the scenario, mirrors any of the level of facilities. Then just also under some considerations for the hierarchy, I guess what's depicted in the figure is quite an ideal scenario where digital twins can be developed for everything, but it's not necessarily always realistic to make digital twins for every single component in a car or every single resource or process and so on. So I guess this hierarchy can change depending on the use case, where maybe sometimes you don't need to mirror a resource or facility, but you just need the products and its processes. Or, for example, as I mentioned, for a product or like a vehicle, maybe you don't need to create digital twins of the wheels, let's say, but maybe just the drivetrain and so on. So yeah, that's just something to keep in mind. So then onto the internal architecture of a digital twin. So all the digital twins that was in the hierarchy conforms to the structure identified. So the general structure is consisting of data, models, and services for a digital twin. So onto the data, it can either be stored within the warehouse attributes or federation attributes. So as I mentioned before, the different types of integration methods. So the warehouse attributes stores all the data that's meant for warehousing and is meant to be stored long term for each digital twin, where the federation attributes doesn't necessarily store the data, but rather all the metadata that's related to a federation request. Then for the DT models, so this is all the models that's contained within a digital twin, with the complexity of the models varying quite a lot. It could be simple rule-based models being used by the services or more complex anomaly detection models. Then onto the services for digital twins. So these are also categorized into either being core services to the system or then custom developed services for the digital twins. So the core services represents all the services for the digital twins that's core to the functioning of all digital twins. So for example, the ingestion and request handler manages all the requests coming into a digital twin and the data being ingested. The warehousing and federation services manages those two types of integration methods. So for example, interacting with the attributes or answering requests and so on, extracting data from the attributes and sending it back to a query. Then also for the data conformity service, so this is a service that makes use of the data or digital twin models, extract the model and determine whether the data is complete or correct depending on what model is used. So for example, maybe applying a data schema towards the data to see if it conforms to the schema. Yeah, and then also one thing to mention, this type of structure can be developed for a single digital twin instance, or then how we applied it is on more of a type level. So instead of creating the structure for every single, let's say, engine being built in a factory, you just create a type of the structure and that manages all the instances related to the type. Then just also onto an illustrative example. So the paper goes into a bit more detail on this example, but broadly speaking, the illustrative example follows the production of a high voltage battery. So in this scenario, there's only also products and processes being mirrored within the hierarchy, where the high voltage battery is represented as an assembly digital twin, and then the modules are the components related to that assembly. Then just also onto the processes. Two types of processes are applied to the battery, which is the charging and measuring processes, and then also a spot welding process applied to the module. So in this scenario, there's a couple different, or in the illustrative example, there's a couple different scenarios being followed. So it's the warehousing and federation approach. So in this case, the product digital twins follow a more warehousing integration, primarily warehousing integration approach, and processes follow a federation approach. So in the scenario, when data is captured by the different sources, so at the bottom there's a product source system, the data is captured from the sources, published and then ingested by the product source adapter. The product source adapter in that case then performs some initial transformations if required, maybe transforming data from XML to JSON or something as a simple example. Then trying to classify the data is also an important function of this component. So for example, using a part code or part number and so on to classify to what digital twin the data belongs to. So it does this through interacting with, let's say, the management services, where the topic directory would house that information. Once it does that, it can publish it to the relevant topics, and the digital twin ingestion handler at the bottom of the internal architecture that I introduced a couple of slides before would ingest that and then send it to the relevant warehousing service, at least for the product side of things. And then it can be stored long term and then also be checked by the conformity service. So when a request for data comes in for that warehouse data, it's quite simple as the data is already ingested and stored within the digital twin. But in the case of federation, so for the process digital twins, this might not be as simple as the data isn't necessarily already within the source when the request comes in. So there's a couple of additional components. So for example, in the data source directory, it would contain the semantic mapping, as I mentioned before, which is describing where the data is, what the data looks like within the sources. So when a request for the process data comes in, the digital twin needs to interact with the data source directory to determine to which source adapter, which manages the interactions between the digital twin system and the source adapters or the source systems. So yeah, that's just, I guess, two different approaches for ingesting and querying data. Then just on to the preliminary evaluation that was done in the paper. So at the time of writing the paper, complete evaluation and functional verification wasn't done. So we just did a quick preliminary evaluation, but since then it's been finalized, and we aim to extend it to a journal paper to include the more, I guess, final evaluation. So the preliminary evaluation was done in terms of functional and non-functional requirements, which is also introduced in the paper. I didn't really discuss it too much in the presentation, but what I would like to discuss is the design principles that the architecture adheres to. So first of all, it's specialization versus generalization. So this is addressed by the use of the TDTA and digital twin instance concept. So a digital twin would remain as general as possible until specialization is required. So in the scenario, let's say a TDTA would manage all the interactions and requests coming in until the request becomes too much. So the TDTA might become like a bottleneck in the scenario, or then also maybe in a scenario where the request becomes too specific to a single digital twin instance. Then just also the mirror of the world of interest. So this is addressed through setting or developing the digital twin hierarchy and developing digital twins specific for the different types of products and then the different types of production digital twins. Then just self-similarity is addressed by the different digital twins all having similar external interfaces. So it doesn't necessarily matter where the digital twin is within the hierarchy, all the other digital twins can interact with it. And then just finally, the complexity of interactions is addressed by keeping all the complex interactions internal to the digital twins and then also the source adapter, and then also using the management services as a dedicated service for managing all the interactions between the digital twins. Yeah, and then just to conclude, the paper presents an architecture for a system of digital twins to integrate product and production information into the relevant digital twins within a large automotive manufacturing enterprise. It does this through the development of a digital twin hierarchy that includes the relevant digital twins, a preliminary evaluation in terms of the functional and non-functional requirements show that the architecture meets these requirements and that the architecture also adheres to the generally applied design principles. And then just finally, the proposed digital twin system aims to address the gap in research on the interaction and integration between digital twins within the production environment through developing of specific product and production digital twins and identifying the relationships between them. So it's envisioned that this integration would then allow for a variety of new use cases and also explain the effect that the production environment would have on a product and then also vice versa. So yeah, that's all from my slides. Thank you, everyone.